get to it. All of the study stuff you need is online. So just remember when you're studying to not just be satisfied with saying, oh yeah, I remember like the definition of a critical value, right? That's not an appropriate way to study for this class, right? You should say, oh, what is a critical value? Why is it a critical value? What does that mean? What would that look like in a graph? How would I interpret that in terms of a word problem? And right? Like you could probably keep coming up with a couple more questions to ask yourself to interpret anything and everything surrounding just that one idea, okay? And so that's how you should be approaching your studying. Now, something that I thought was kind of cool and that came to mind after last Friday when I showed you the video or a graph of the inverse tan function, and that like got crickets in the audience. So I thought we could at least momentarily think about the idea of an inverse function because we haven't done that in a serious way, and use some of our tools to talk about. So what we've done, right, on the mastery test at least, was to memorize some formulas for the derivative of an inverse trig function, right? But we never talked about how you would find a general formula for the inverse of any function, right? For the derivative of the inverse of any function. So I thought we could use our tools to do that really quickly. So this is sort of unrelated, but a nice reminder of the things that you should know come test time. So if we have an inverse function, y equals f inverse of x, and my goal is to find the rate of change of this function, okay, and that's all I've told you, then what we can do is remind ourselves that, okay, well, if y equals f inverse of x, that means that f of y equals x, right? This is the relationship between a function and its inverse. Is that ringing a bell? Maybe? Okay. So the roles of the inputs and the outputs swap. Okay. So if I'm here and I'm looking for a derivative, then what I have on the left-hand side is a function composed with a function of x, right? Because y, remember, was some function of x. In fact, it was the inverse function of x, right, for this f that we're starting with, okay? So on the left-hand side, I have a composition of functions. So how do you take the derivative of a composition of functions? The chain rule, exactly. So the chain rule would tell me that the derivative of this left-hand side with respect to x is what? How does the chain rule work? Great. Exactly. Okay. And then what's the rate of change of x with respect to x? Can I get more than 3 people to answer? What's the rate of change of x with respect to x? 1, right? Okay. So there's that. Okay. So what was my original goal in setting out? We started with this function, the inverse function of f, and I wanted what? I wanted the rate of change function for y, right? That's what I said I wanted. So notationally, that looks like y prime, right? So I've introduced a y prime here. That's what I want, so I'm going to go ahead and solve for it. And then, but notice, right, I've got, this is a function of y, essentially, right now. And since I started with a function expressed in terms of x, it would be nice if I could end up with something like that. So what I can do is I can say, oh wait, y is f inverse of x, and go ahead and substitute that back in for y. So we get this. Okay. So what we've just done is derived, or proven, if you will, a formula for the derivative of a general inverse function. Okay? So rather than specifically looking at the inverse of tan or the inverse of sine or the inverse of cosine, right? Now we're looking at the inverse of f, right? And we've derived a derivative formula for any inverse function. Okay? Now, what's one catch to this? So if we're thinking about functions, is there a place where this function could ever be undefined? Like, is this function good always? What could go wrong? It could have a 0 on the bottom, right? So this holds as long as this composition in the denominator is non-zero, right? Okay. So this comment that I've made, okay, so before I move on, so this seems kind of random, okay? But this was what I thought was a nice way to remind you, first of all, that you do know things about inverse functions, but secondly, that we can use our tools that we've developed. So in particular, what tool did I use here to prove this formula? What did we do? We used the chain rule, and we also did implicit differentiation, right? So we've used implicit differentiation as one of our tools because, right, when I had f of y equals x, I had an equation relating two variables, right, two quantities. And I differentiated that equation relating the quantities, okay? So this is implicit differentiation, employing the chain rule along the way in order to establish this formula, okay? This isn't something I expect you to memorize. This is just something that can show you the strength of the tools that we've established, okay? Now, this last comment I think is particularly interesting because we haven't talked about that much, right? So I said, you know, hey, we found a formula for a derivative for the inverse of a generic function, right? But we have a catch. This derivative only exists as long as this denominator is not 0. We've never had a conversation like that before, right? Every time we've looked for derivatives, we've just assumed that they always are there, right? So that's something that I want to talk about today, which is, you know, are we always guaranteed to have a derivative, right, for every value of x? So let's take a look at some pictures. So before we dive straight into that, I want to make sure that we understand graphically. So this is a little bit of review. I know I said I would totally move forward, but I feel like if we can for sure do this, then hopefully the rest of the day's conversation will make a lot of sense. Okay, so what I want you to do is to take this curve and imagine that this is the curve of the rate of change of a function f, okay? So this is the rate of change function, and I want you to draw or sketch roughly the corresponding accumulation function given that it goes through this point, okay? So let's say that this point, 0, 2, is on the graph of your accumulation function, and this purple graph is the graph of your rate of change function, okay? So I want you to use all of the tools that we built up last week to roughly sketch the curve of f of x, y equals f of x. Okay, so that's your task. You can talk to a neighbor to reason your way through it if you'd like. All right, you guys ready? What's some of the easiest things that you can pinpoint right away? Critical points. How do you find critical points? Where the derivative is 0. So that happens at which x values? -3, 0, and 2. So I should potentially have maxes and mins at those 3 x values. Will I have maxes and mins at those 3 x values? Yes. How do I know? By looking. The sign of the rate of change changes, right? So if the rate of change is negative, then that means that my accumulation function is doing what? Decreasing. And then from here to here, my rate of change function is positive, so that means my accumulation is increasing. So if my accumulation switches from decreasing to increasing, then I will have a local minimum, okay? And then likewise at 0, so let me start at 0 for real. So to the left of 0, the rate of change is positive. To the right of 0, the rate of change is negative. So what should it look like around this point? To the left, I should be doing what? The accumulation function is increasing because the rate of change is positive. And to the right, I'm decreasing, or the accumulation function is decreasing because the rate of change is negative. Notice the whole time from about this x value to this x value, the rate of change is decreasing. So that tells me that my accumulation function should be concave down. Okay, so something like something like that. Okay, and then but I'm still, let's see, so from here to here, my rate of change is negative, but it's increasing. So that means my accumulation function will be decreasing and concave up. So that makes this x value, or this point, what kind of point? An inflection point, because the concavity changes, right? Okay, and then so then I'm going to have like a local minimum at 2, right? And then to the right of 2, what is the rate of change? It's positive and increasing, so the accumulation function will be increasing and what? Concave up. Up like a cup, okay? And then let's see, so we were still increasing over here, but let's see, so let's see, from -3 to -2. I should be concave from -3 to -2. The rate of change is doing what? Increasing or decreasing? The rate of change is increasing. So I should be so the accumulation function should be concave up, and it's positive. So sorry, the rate of change is positive, so that means the accumulation function should be increasing. So increasing and concave up looks like something like that, right? And so once again, over here we have an inflection point, okay? And then to the left of -3, the rate of change is negative and increasing. So the accumulation function is doing what? Decreasing and concave up. So we have a local minimum. Okay? So that's roughly what your graph should look like. Here's a twist. What if instead of the purple graph being the rate of change function, what if it was the original function? What if it's the accumulation function? Can we do the same process? We could, right? So in particular, we're going to do this a heck of a lot faster, okay? So if the purple graph is now the accumulation function, what are some easy places? Will it be okay if I delete what I've got up here? Okay, so now the purple graph is the accumulation function. What are easy places to identify the rate of change function? Maxes and mins. So right around here, there's a max, and right around here, there's a min. So what do I know about the rate of change function at those values? Those x values. The rate of change should be 0. Okay? In between this x coordinate and this x coordinate, what is the accumulation function doing? It's decreasing. What does that tell you about the rate of change? Should be negative. Negative. Okay? And then to the left of this x value, right? What is the accumulation function doing? It's increasing. So what does that tell you about the rate of change? Should be positive. And then likewise, to the right of this x value, the accumulation function is increasing. So the rate of change should be positive. Now, how do I know that it's not positive like that? How do I know? Shay? Beautiful. Okay, so the fact that the purple graph is concave up means that the rate of change function is increasing. So the rate of change can't like suddenly shift and start decreasing, right? It has to continue increasing. So it's beautiful. Okay? Okay, so that gives you some practice, hopefully some really solid practice in thinking about how these are all related. Okay, so the rate of change and the accumulation, and then the rate of change, all good times. Now, now I have this guy. So let's say that this is your accumulation function. Taylor, how you doing? Good. What are we talking about? I did. Okay. They can wait till after class. Thank you. So, okay. So if I look at this graph, right, and I want to talk about the rate of change, let's talk about what's the rate of change at negative 1.5. How would I figure that out? So I heard somebody shout out slope. Okay. Well, why does that work? How did we define rate of change? Changes in y over changes in x, right? So at negative 1.5, right, I could pick like, a little bit away from there, another x value, and then compute the change in y relative to the change in x. Now these are equally scaled axes, and so these are equally spaced. So that means that I've got like negative some change in y. This is the change in y here. This is the change in x here. And their relative sizes are what? The relative size of the change in y to the change in x is if you were to measure the change in y using the change in x, what would you get? 1? How about -1? So in magnitude, they're the same size, right? But when we talk about changes, we have to take into account whether or not it's giving you a positive or a negative value, right? So the change in y is a negative value corresponding to this positive change in x. So the relative size will be -1. Okay, so over here, on this, and if we did that for any x value over here, right, we'd have a rate of change of -1. What if I do it on this right-hand side? We'll get a rate of change of +1. Okay, what about at 0? So if I go a little bit to the right and compute the average rate of change, I get +1, right? But if I go a little bit to the left, I get a rate of change of -1. So which one is it? So here's the kicker, right? Whenever we've talked about the rate of change function, we say the rate of change function. That means for any x value, you can only have one corresponding output, right? And I just introduced a scenario in which there could be more than one, right? That's bad, okay? So if we're going to talk about the rate of change function, it can't include this value at x equals 0, right? There's too many choices for what you could have as the rate of change there, okay? So when you get this sort of like corner effect, this sharp corner in a graph, right, there's the derivative is undefined there, okay? So undefined rate of change at x equals 0. Question? That's exactly what I just said. Yep. That's what we just said, right? So we'll look at one more example, right? Something like this. So we've got a cusp here, right? So that's what this, when it comes curved into a point, that's called a cusp. And it's the same type of situation, okay? So at this value at x equals 0, the derivative of this function, if I'm considering the purple graph an accumulation function, would be undefined. Okay. All right, so I've introduced to you now this idea that derivatives don't have to be defined everywhere, right? Even if a function is. Okay. Now, one picture that I didn't draw would be something like this. If my accumulation function looked like that, right? So if this is the graph of my accumulation function, it's defined piecewise, right? It's this piece and then this piece. So it's defined, the accumulation function is defined for all x values up to -1 and then including and after +1. Could I talk about the rate of change of 0? Absolutely not. There's no function there to talk about, right? So this would be another example of a time when you wouldn't be able to talk about the derivative of a function at every x value, right? Because the function isn't even defined at every x value, okay? So there's certain requirements to be able to talk about a derivative, right? You need for the function to exist, right? And then you need for it to behave in a nice way, right? Nice meaning you can find a unique average rate of change, right, over small intervals, okay? All right. That brings us to this really cool theorem, which I have very little time to talk about, but that's okay. Okay, so the mean value theorem gets people in trouble. Okay, so let me give you an example. So the speed limit on the Florida Turnpike is 65 miles per hour. Henry went through a toll plaza on the Turnpike, and his receipt stated the time as being 11:47 a.m. He went through a second toll plaza that is 52 miles away, and his receipt stated the time as 12:32 p.m. When Henry paid the attendant the toll, the attendant handed Henry his change and handed him a speeding ticket. Why did that happen? All right, so if we think about it, right, you could compute, what could you compute given the data that we have? You could compute his average speed. Go ahead and do that really fast. What is his average speed? So 52 miles. That's 45 minutes, right? So 3/4 of an hour. What's his average speed? Does anybody have a calculator? 69. So we'll say about 69 miles per hour. Was he speeding? That's pretty strict, huh? Okay, okay, so let's think about this though. So if his average speed was 69 miles per hour, does that mean that he actually went 69 miles per hour? Okay, so you guys have some ideas about what's going on here, right? So if he was at the toll booth, that means he was stopped, right? And then he had to speed up and then slow down to stop at the second toll booth, right? And then somehow over that period of time, he achieved an average speed of 69 miles per hour. So intuitively, the argument goes, well, he was going slower than 69 miles per hour for some of the time, and then he had to be going faster if the average is going to come out to be 69, right? So Henry fought the ticket in court. He said no one actually witnessed him going 65 miles per hour, but he lost, right? And so this argument that we just gave is the reason why, okay? Henry's real smart, and he tried to appeal. He said, well, even if he did break the speed limit, it was just for a moment. He swore that he went 65 miles per hour for most of the distance between the plazas. The judge doubled his fine. Why did he do that? Oh, wait, what? No, that's not why. So if it's the average and he was going 65 most of the time, then he had to go really darn fast for a moment in time to pull up that average to 69, right? Okay, so there are some assumptions that we're making in order to have this conversation. The most fundamental conversation or assumption is that modeling his position is a continuous activity, right? But that seems very reasonable. We're talking about position over time. Time happens in continuous. That's cool. Okay. Now, we're also assuming that we can talk about his velocity in a, we can differentiate his position to talk about his velocity. Now, here's, I'm not going to be able to do that. Okay, so here's the idea behind, I'm not going to be able to show you all these because of time. Here's the idea, okay? So we have an accumulation function, okay? And we have some time interval, right? So here's, when Henry got through the first toll, and here's when Henry got through the second toll. And his position changed from some distance here to 52, so this change right here is a change in 52 miles, okay? But I would compute but in reality, right, in the more general scenario, this would be the change in outputs, right? So I could compute the average speed by doing change in y, right, over change in x. Okay, so this would be the average speed, which we would represent as some, hypothetical scenario in which he drove at a constant rate the entire time, right? And so what the mean value theorem does is guarantee that under certain conditions, namely the ones that I mentioned just a minute ago, there will be a moment in time, right, somewhere between A and B, where the instantaneous rate of change has the same value as the average rate of change. Okay, so we'll call this some value C, and at that moment, C between A and B, the instantaneous rate of change is equal to the average rate of change. Okay. So once again, though, in order to talk about this, there are certain requirements, and it's required that the derivative exists everywhere between A and B in order to make this claim. Okay. Some of the slides that I don't have time to show. Oh, no, I do still have time. I was looking at the wrong clock. Yay. Okay, so let me show you some pictures of what will break this. Okay, so we require the function to be continuous over the closed interval, and we require that the derivative exists for what I just said to happen. And that's because if we don't have that, then we can't make these conclusions. So what I've got here is an animation of an accumulation function in red. It's definitely continuous, right? I could draw it in one fell swoop. But at x equals 0, it's not differentiable. Okay, so if I were to consider this interval between like negative 0.35 and positive 0.4, okay, I could compute the average rate of change, and I'm visualizing that with this secant line, right, this line connecting those two values. Okay, so the slope of that line is the value of the average rate of change over that interval. But notice that I've got this animation with this blue line, and the blue line is showing us the tangent line to every point along the curve. Okay, so the slope of that line represents what? The rate of change at that particular x value. Okay, so what we're looking for is whether or not this blue line sort of becomes parallel, if you will, to the black line segment, right? Did it? No, right? So this is an example of a function that doesn't satisfy the conditions necessary to use the mean value theorem, okay? Which again just says if your function is continuous and it has a derivative over the entire interval, okay? So again, this example breaks it at x equals 0 because it's not differentiable at 0. But if those two conditions were satisfied, then there should be some value in the interval where the rate of change at that value is equal to the average rate of change over the interval, okay? And that's what lets people get speeding tickets. Bad news. Here's another example, right? So this is not a continuous function, so it does not satisfy the requirements of the mean value theorem, okay? And you can see that at no x value did it work, if you will. So let me just one more time make sure that you have the image. So a visual image. If this is your accumulation function, right, and you have some interval, then you can compute the average rate of change over that interval, right? And that would be the slope of this secant line. And what the mean value theorem says is there is some x value in between A and B, at least one, there could be more than one, but at least one x value where the tangent, right, the rate of change at some moment, so here's one place, and actually there, in my picture, there is more than one, right? Maybe about here would be another place, so there's another c value, right? But it says that there is some c value where the rate of change at that value is the same as the average rate of change over the interval. Okay? All right. That's the mean value theorem, guys. Cool. I'll see you on Wednesday. Oh, for recitation, hopefully you've been studying, so hopefully you have questions. And so the main goal of recitation for this week is to address your questions in preparation for the test. Okay?